Somewhere in the Southern Ocean, roughly 26 million years ago, the sun rose over a world that would be unrecognizable to us today. The water was colder, the continents were shifting, and somewhere near the surface of that ancient sea, something moved. Something so large that the word large almost loses its meaning. Picture a creature the length of 3 school buses parked end to end. A tongue that weighs as much as a full-grown elephant. A heart the size of a small car, pumping, beating, pushing blood through arteries so wide a child could crawl through them. This is not a monster from science fiction. This is not a myth. This is a real animal. And on this particular morning, it is dying. We don't know exactly how it happened. We may never know. But what we do know, drawn from decades of fossil analysis, biomechanical modeling, and cutting-edge isotope research, is that nothing like this animal has ever existed before in the 500 million year history of complex life on Earth. And the evidence strongly suggests nothing like it will ever exist again. This is not just the story of one creature's final hours. This is the story of a biological limit, a ceiling built into the laws of physics, ecology, and evolution itself. A ceiling that even the most extreme forces of natural selection cannot break through. We are talking, of course, about Patagotitan majorum, the largest dinosaur ever discovered, with a body mass estimated at up to 76 metric tons. No, wait, stop. That's not the largest animal that ever lived. That's the largest land animal. And the distinction matters enormously, because the true record holder doesn't walk. It doesn't fly. It doesn't crawl across ancient plains leaving footprints the size of bathtubs. It swims. Or rather, it swam. Past tense. Because the animal we're investigating today is the blue whale. Balaenoptera musculus. A species still alive right now, in our oceans, at this very moment. A species that, in its largest confirmed specimens, reaches 33 meters in length and 190 metric tons in body mass. A species so extreme in its dimensions that scientists still argue about how it functions, how it breathes, how it hunts, how its heart doesn't simply tear itself apart under the pressure of its own beating. And here is the thing that should stop you cold. We almost lost it entirely. Not 26 million years ago, not in some prehistoric catastrophe we can only read in stone. We came within a few decades, within living human memory, of hunting this animal to extinction. The largest creature ever to exist on this planet was nearly erased not by an asteroid, not by volcanic winter, not by the grinding gears of evolutionary obsolescence, but by exploding harpoons and factory ships. In the 20th century alone, whalers killed an estimated 360,000 blue whales in the Southern Ocean. 360,000 individuals of the largest species in Earth's history. Gone. Rendered into oil and fertilizer. The global population, which scientists estimate may have once numbered 250,000 individuals, had collapsed to perhaps 450 animals by the time the International Whaling Commission banned commercial blue whale hunting in 1966. 450 animals. The most massive creatures the biosphere has ever produced, reduced to a number smaller than the audience in a mid-sized theater. But this video is not primarily about that tragedy, though we will return to it. This video is about something deeper, something stranger,
something that the near extinction of the blue whale forced scientists to confront with new.
Why is the blue whale so impossibly large in the first place? Why did evolution push one lineage of mammals to this particular extreme and no further? And what does the answer reveal about the hidden architecture of life on Earth? The invisible rules that govern what can and cannot exist? Because when researchers began asking those questions seriously, beginning in the 1990s and accelerating dramatically through the 2000s and 2010s, they discovered something unexpected. The blue whale is not just the biggest animal. It is an animal living right at the absolute edge of biological possibility. A creature that has pushed against every physical and physiological constraint that evolution allows, and stopped there, at the very boundary, as if it knows what lies beyond: extinction. So today, we are going to spend 6 hours with one blue whale, a mature female somewhere in the Southern Ocean. We are going to watch her feed and breathe and move through water, and we are going to understand, piece by piece, why every single thing she does reveals something profound about the nature of size itself. Why bigger always costs more than you think. Why the ocean made giants possible, but only up to a point. And why, above all, this animal represents a kind of biological miracle that the Earth, under current and foreseeable conditions, is extraordinarily unlikely to produce again. Let's begin at dawn, 6 hours before the end. And let's start with the most fundamental question of all. How does something this big even exist? The architecture of the impossible. To understand why the blue whale exists at the size it does, you first need to understand what size actually costs. We use the word big casually. We say a building is big. We say a storm is big. But in biology, size is not a description. It is a transition.
Every increase in body mass comes with a precise biological invoice, and that invoice must be paid in full every single day, or the animal dies. Here is the fundamental rule that governs all life on Earth. It is called Kleiber's Law, named after the Swiss biologist Max Kleiber, who first formalized it in 1932. The rule states this: as body mass increases, the metabolic rate required to sustain that body does not increase at the same rate. It increases more slowly. Specifically, metabolic rate scales to body mass at roughly the 3/4 power. What does that mean in practice? It means that larger animals are, in a sense, more efficient than smaller ones. A blue whale does not need 1,000 times more food per kilogram of body weight than a mouse. It needs considerably less, proportionally speaking. This is one reason why large body size can be evolutionarily advantageous. Bigger animals get more out of every calorie. But, and this is critical, the absolute caloric requirement still increases with size, enormously. A blue whale must consume between 1.5 and 3 million kilocalories every single day during feeding season. To put that in terms you can feel, the average adult human requires roughly 2,000 kilocalories per day. The blue whale needs the equivalent of 1,500 to 3,000 human daily portions every day. And it must obtain all of those calories from one of the smallest animals in the ocean: krill, Euphausia superba, a crustacean barely 5 centimeters long, weighing less than a gram. Translucent, swarming in clouds so dense they turn the surface of the Southern Ocean orange-red. And the blue whale, this 33-meter, 190-ton colossus, has evolved the most extraordinary feeding mechanism in the history of vertebrate life, specifically to harvest these tiny creatures in industrial quantities. The mechanism is called lunge feeding. And when you understand how it works, truly understand the physics and the biomechanics, it becomes one of the most astonishing things in all of natural history. Our whale, let us call her what the research teams call large mature females in the Southern Ocean, a Category A individual, surfaces at first light. She has spent the night in relatively shallow water, conserving energy, her metabolic rate reduced to its resting minimum. Now the sun is climbing and the krill are responding to light, aggregating in dense patches near the surface and at depth. Her task for the next several hours is simple to describe and almost incomprehensibly demanding to execute. She must eat enough krill to keep herself alive, and to do that, she must lunge. Imagine accelerating your entire body, all 190 tons of it, from near standstill to approximately 11 kilometers per hour in just a few seconds. You open your mouth to an angle of approximately 80 degrees, nearly a right angle, and you engulf a volume of water and krill that, in a single gulp, can exceed 90 cubic meters. 90 cubic meters! That is roughly the volume of a small house, taken into the mouth in a fraction of a second. The water then has to go somewhere. It cannot be swallowed. It must be filtered. The whale's baleen plates, those long, fringed keratin structures that hang from the upper jaw like the teeth of an enormous comb, trap the krill while allowing the water to escape. But before that filtering can happen, the whale must decelerate the entire engulfed mass, close its mouth, and push the water out with its enormous tongue. A tongue, remember, that itself weighs approximately 2 to 3 tons. The entire lunge sequence takes less than 10 seconds. And here is what makes this not just impressive, but scientifically staggering. Research published in the journal Science in 2021 by a team from Stanford University, led by biomechanist Jeremy Goldbogen, used biologging tags, sophisticated electronic devices attached to living whales, to measure the energetic cost of lunge feeding with unprecedented precision. What they found was extraordinary. A single lunge feeding event in a blue whale yields a caloric return of approximately 190 times the energy expended in the lunge itself. 190 times! The profitability of a single feeding event is almost unimaginable. But, and here the physics becomes merciless, this extraordinary efficiency only works when the krill are dense enough. When the swarm is sparse, the energy equation flips. A lunge through low-density krill can cost more energy than it returns. The blue whale is not a grazer. It is a precision striker. It must find the densest, most concentrated patches of krill in the ocean, and it must hit them with extraordinary accuracy, or it starves. This is the first hint of the ceiling we mentioned in the opening. The blue whale's size gives it extraordinary feeding efficiency when conditions are right, but it also makes it utterly dependent on those conditions being right. There is no fallback. There is no alternative prey. There is no good enough. At this size, in this ecosystem, the margin for error is vanishingly small. Our Category A female makes her first lunge of the morning at approximately 6:47, roughly 5 hours and 13 minutes before the moment we are building toward. The krill patch is good, dense, exactly the concentration her sensory systems, we will discuss those shortly, have guided her toward. She rolls slightly to the left as she hits the swarm, a characteristic behavioral quirk documented repeatedly in blue whales by researchers at the Cascadia Research Collective in Olympia, Washington. The lunge is clean, efficient. She processes the water in 8 seconds, closes her mouth, and is already repositioning for the next strike. For the next 40 minutes, she feeds almost continuously. Lunge after lunge. The biologging data from similar events compiled by Goldbogen's team and published in the Proceedings of the Royal Society B suggests she will make between 300 and 400 lunges in a full feeding day. Each one a precisely calibrated explosion of energy and recovery. And while she feeds, her body is doing something else, something that researchers only began to fully appreciate in the last 2 decades. Her body is managing a thermal crisis. Here is a problem that almost no one outside of marine biology thinks about when they picture a whale. You are generating enormous amounts of heat. Your muscles are working at extraordinary intensity. You are a warm-blooded mammal in cold water, and you are wrapped in a layer of blubber, evolved precisely to prevent heat loss that is now threatening to cause dangerous overheating during peak activity. Research by Andreas Fahlmann at the Oceanographic Research Institute in Valencia, Spain, published in 2018, demonstrated that blue whales have evolved a sophisticated network of countercurrent heat exchange systems in their fins and flukes, specialized vascular arrangements that allow them to dump excess heat into the surrounding water without losing the core warmth they need to survive. It is, in essence, a biological radiator system, and it has to work perfectly, continuously, at every point in the feeding cycle. One system malfunctions, the whale overheats. The whale dies. You begin to see the pattern. At this size, everything is right at the edge. There is no redundancy. There is no slack. Every system is maximally optimized, maximally stressed, and operating with margins that would terrify an engineer. And we have not yet talked about the most obvious system of all. You are 190 tons of air-breathing mammal. You are spending much of your time underwater. The physics of gas exchange, the movement of oxygen into the blood and carbon dioxide out, is constrained by the size of your lungs, the surface area available for diffusion, and the time you have at the surface between dives. Blue whales breathe approximately 1 to 4 times per minute at rest, and somewhat more frequently during active feeding near the surface. Each breath exchanges approximately 90% of the lung's air volume. For comparison, humans exchange only about 15% of lung volume in a normal breath. The whale's respiratory efficiency is extraordinary, but it is also, again, right at the boundary of what is physically possible. Now make the animal bigger, significantly bigger. Say, twice the mass of a blue whale. Suddenly, the lungs cannot scale efficiently enough. The time required to surface, breathe, and return to depth becomes prohibitive. The oxygen requirements of the larger muscles exceed what the respiratory and circulatory systems can supply. The heart, already the size of a small car in our actual blue whale, would need to be larger still, requiring more oxygen itself, creating a feedback loop that spirals toward impossibility. This is the wall, the physical, physiological, thermodynamic wall that stands at the upper limit of vertebrate size in the ocean. The blue whale has not hit this wall. It has not crashed into it. It has, over millions of years of evolution, approached it with extraordinary precision and stopped just before it. Or has it? Because there is a question that has divided marine biologists for decades. Is the blue whale at its evolutionary maximum? Or is it simply at the maximum permitted by current ocean conditions? Could it, under different circumstances, different ocean temperatures, different prey distributions, different predation pressures, evolve to be even larger? The answer to that question requires us to go back in time, much further back than the blue whale's own evolutionary history, back to the moment roughly 53 million years ago when the ancestors of all cetaceans, all whales and dolphins, made one of the most dramatic ecological transitions in vertebrate history. They walked back into the sea. And what happened next explains almost everything about why the blue whale is the size it is, why the ocean is the only place on Earth where this kind of size is possible, and why, when the conditions that made the blue whale possible began to shift, this species found itself facing a challenge that even 3 million years of evolutionary refinement had not fully prepared it for. But before we get there, we need to spend a moment with our whale as she pauses between feeding bouts at the surface, breathing. Because in these few seconds of stillness, watching her exhale, that column of warm, moist air rising 6 to 9 meters into the cold southern morning, you can see the entire problem of being the largest animal in the history of life on Earth compressed into a single, visible act. She breathes. She must. And every breath is borrowed time. The road to gigantism. 53 million years in the making. To understand the last 6 hours of the largest animal that ever lived, you need to understand the journey that created it. 53 million years ago, on the warm, shallow coastlines of what is now Pakistan and India, a small four-legged mammal was doing something unusual. It was wading, paddling, spending increasing amounts of time in water. It looked, in some reconstructions, vaguely like a cross between a wolf and a tapir. It was not impressive. It was not large. It weighed perhaps 25 to 30 kilograms. Its name, given to it by paleontologists who found its fossils in the Kuldana Formation of northern Pakistan in the 1970s and 80s, was Pakicetus. Pakicetus is the oldest known ancestor of all cetaceans, all whales, all dolphins, all porpoises. Every single one of them traces its lineage back to this modest, semi-aquatic creature on an Eocene shoreline. The fossils were first described in detail by Philip Gingerich of the University of Michigan, whose work through the 1980s and 90s transformed our understanding of whale evolution. What Gingerich and his colleagues found in those Pakistani rock formations was extraordinary. A nearly complete sequence of transitional forms showing step by step the transformation of a land mammal into a fully aquatic one. Within roughly 15 million years of Pakicetus, an eye blink in geological time, the cetacean lineage had produced Basilosaurus, an animal that was fully aquatic, fully committed to the ocean, and already large, very large. Basilosaurus reached lengths of up to 20 meters. It still had tiny vestigial rear limbs, useless for locomotion, but preserved as evolutionary echoes of its terrestrial past. Its fossils have been found in Egypt, the United States, and Pakistan, and are currently displayed in museums including the Smithsonian National Museum of Natural History in Washington and the Egyptian Museum of Natural History in Cairo. But here is the critical thing about Basilosaurus, the thing that sets the stage for everything that follows. It was not a filter feeder. It had teeth, real teeth, differentiated teeth, the teeth of a predator. It hunted individual prey items. It was, essentially, a very large marine reptile-like predator that happened to be a mammal. The filter feeding strategy. The strategy that would ultimately allow whales to reach the size of blue whales had not yet evolved. That revolution came later, and it came from a catastrophe. Approximately 34 million years ago, the Earth underwent one of the most dramatic climate transitions of the Cenozoic era, the Eocene-Oligocene boundary event. Global temperatures dropped sharply. Antarctica, which had been relatively temperate and partially forested, began its transformation into the ice-covered continent we know today. The Drake Passage, the seaway between South America and Antarctica, opened fully, allowing the Antarctic circumpolar current to establish itself for the first time. And that current changed everything. The Antarctic circumpolar current is the largest ocean current on Earth. It circles Antarctica continuously, driven by wind, creating a system of upwelling that pulls cold, nutrient-rich water from the deep ocean to the surface. This upwelling fertilizes the surface waters with phosphorus, nitrogen, silica, the raw materials of photosynthesis. Phytoplankton bloom in extraordinary quantities. Zooplankton, including krill, explode in response. The Southern Ocean becomes, in ecological terms, a food factory of almost incomprehensible productivity. But this food is packaged in tiny units: krill, copepods, small crustaceans measured in millimeters and centimeters, individual prey items so small that a large predator hunting them one by one would expend more energy in the hunt than it could ever recover from the meal, unless it evolved a way to harvest them in bulk. This is the evolutionary pressure that produced baleen. The precise timing and mechanism of baleen evolution is still actively debated in the scientific literature. Research published in the Proceedings of the Royal Society B in 2017 by Felix Marx at the Royal Belgian Institute of Natural Sciences and colleagues proposed that early baleen whales may have passed through a stage of raptorial suction feeding before developing true filter feeding. Other researchers, including Mark Ewan at George Mason University, have argued for a more direct transition from toothed ancestors. What is not debated is the outcome. By approximately 23 to 28 million years ago, true baleen whales, mysticetes, had evolved and were diversifying rapidly. They had found the key that unlocked the Southern Ocean's extraordinary productivity. And once that key was turned, the door to gigantism swung open. But not immediately. And this is the part of the story that surprises most people. Blue whales are not ancient giants. They are not some primordial leviathan that has haunted the oceans since the age of dinosaurs. They are, in evolutionary terms, remarkably recent, strikingly recent. The largest body sizes in mysticete whales, including the blue whale, the fin whale, and the bowhead whale, appear in the fossil record only within the last 3 to 5 million years. Research published in the journal Proceedings of the Royal Society B in 2017 by Graham Slater at the University of Chicago, Nicholas Pyenson at the Smithsonian Institution, and colleagues used phylogenetic modeling to demonstrate that extreme gigantism in baleen whales evolved not gradually over tens of millions of years, but in a geologically sudden burst beginning roughly 3 million years ago. 3 million years ago. That is when the ice ages began in earnest. That is when the glacial-interglacial cycles started producing the seasonal patterns of ocean productivity that we recognize today. That is when krill began to aggregate in the dense, concentrated, predictable patches that make lunge feeding so extraordinarily profitable. The blue whale did not evolve to be large and then find krill. It evolved to be large because krill became available in the right way at the right time. The ocean's seasonal patchiness, the way nutrients and prey concentrate in specific regions during specific seasons, is what made the blue whale's feeding strategy possible. And the feeding strategy is what made the size possible. This is the insight that Slater, Pyenson, and their colleagues described as a trophic cascade to gigantism. The physical restructuring of ocean productivity over the last 3 million years effectively built the ecological niche that the blue whale then evolved to fill. The animal did not create the niche. The niche created the animal. And here is where the story takes its first dark turn. Because if the blue whale's extraordinary size is a product of very specific oceanographic conditions, dense, predictable, seasonally concentrated krill patches in cold, highly productive waters, then those conditions can change. They have changed before, and there is compelling evidence that they are changing right now. But we will come to that. First, we need to understand what those 3 million years of evolutionary refinement actually produced, not just the size, the systems. The extraordinary interlocking biological machinery that keeps a 190-ton animal alive and functioning at the absolute edge of physical possibility. Our whale has been feeding for nearly 2 hours now. She has made somewhere between 60 and 80 lunge feeding strikes. The krill patch she found at dawn was exceptional. The kind of dense aggregation that occurs when cold upwelling water meets a thermocline and concentrates prey vertically as well as horizontally. She has been efficient. Her blubber reserves, drawn down during the long migration from tropical breeding grounds to Southern Ocean feeding grounds, are beginning to recover. But she is also dealing with a problem that her ancient ancestors never faced. A problem that has nothing to do with physics or physiology. She is alone. Blue whales are not reliably social animals. They do not form stable pods in the way that sperm whales or orcas do. They communicate over vast distances using the lowest frequency vocalizations of any animal on Earth. Calls that register at around 14 to 16 hertz, well below the threshold of human hearing, and that can theoretically travel thousands of kilometers through the deep sound channel of the ocean. Research by Mark McDonald and John Hildebrand at the Scripps Institution of Oceanography in La Jolla, California, published across multiple studies in the Journal of the Acoustical Society of America, has documented these calls in extraordinary detail. What those calls say, what information they carry, whether they represent something we might call language, these are questions that science cannot yet fully answer. What we know is that blue whales call. They call almost constantly. They call at frequencies and volumes that make them among the loudest animals ever documented. A blue whale call can reach up to 188 decibels. For comparison, a jet engine at close range produces approximately 140 decibels. And the calls have changed. Over the past 50 years, as the global blue whale population collapsed under the weight of industrial whaling and then slowly, painfully began to recover, researchers noticed something unexpected in the long-term acoustic records. The frequency of blue whale calls has been shifting downward, globally, across multiple ocean basins. Every year, the calls get slightly lower in pitch. Nobody fully understands why. Hypotheses include changes in ocean noise pollution, forcing frequency adjustments, changes in population density affecting the competitive dynamics of male calling, and, most intriguingly, possible changes related to the recovery of body size in the population as healthier, larger individuals produce lower frequency calls. Our whale calls as she feeds. Deep, resonant pulses that travel outward through the water in every direction. Whether any other blue whale is close enough and listening, we cannot know. What we know is that she is here, at the surface, in the Southern Ocean, on a specific morning in what the research literature would classify as a high-productivity feeding event. And she has approximately 4 hours left. The question we need to ask now is the one that takes us to the heart of this entire investigation. Given evolution has done to make the blue whale possible, 53 million years of transition, 34 million years of oceanographic change, 3 million years of accelerating gigantism, thousands of interlocking physiological adaptations. Why did it stop here? Why is the blue whale the size it is and not larger? The answer is not simple. It is not a single constraint. It is, as we are about to discover, a convergence of limits arriving from multiple directions simultaneously. Physical limits, ecological limits, physiological limits. Each one alone might be surmountable. Together, they form a wall that evolution, for all its ingenuity, has never found a way through. And when we understand those limits, truly understand them, we will understand not just why the blue whale cannot be larger. We will understand why, given what is happening to the world's oceans right now, the blue whale may be struggling to remain as large as it already is. That is the deepest layer of this mystery, and we are about to open it. The wall. Why size has a ceiling. There is a thought experiment that physicists and biologists sometimes use when teaching about scaling. Take any animal. Double its linear dimensions. Make it twice as tall, twice as long, twice as wide. What happens? Its volume, and therefore its mass, increases by a factor of 8, 2 cubed, but its surface area increases only by a factor of 4, 2 squared, and the cross-sectional area of its bones, muscles, and blood vessels increases by that same factor of 4. This is the square-cube law, formulated in its biological context by Galileo Galilei in his 1638 work, Discorsi e dimostrazioni matematiche. It is one of the oldest and most unforgiving rules in all of science. And it means this: every time you make an animal significantly larger, its weight grows faster than the structures supporting that weight. At some point, those structures simply cannot keep up. On land, this law is the primary reason why truly enormous animals are impossible. The largest land animal that ever existed, Patagotitan majorum, weighed an estimated 69 to 76 metric tons and moved with a slow, measured deliberateness that was not a behavioral choice, but a physical necessity. Its bones were already operating near the compressive stress limits of biological material. Its legs were columns, not limbs. Make it significantly larger, and the bones would fracture under the animal's own weight. The ocean changes everything. Water provides buoyancy. It supports approximately 97% of a blue whale's body weight, effectively neutralizing gravity as a constraint on size. This is the fundamental reason why the largest animals in Earth's history have been marine. Remove the tyranny of gravity, and the square-cube law relaxes. The ceiling rises dramatically, but it does not disappear, because in the ocean, different walls appear, and they are every bit as absolute. The first wall is cardiovascular. The blue whale's heart weighs approximately 180 kilograms. It beats at roughly 8 to 10 times per minute at rest, a rate so slow that early researchers using acoustic monitoring equipment initially doubted their readings. During deep dives, the heart rate drops even further, to as low as 2 beats per minute, as the dive reflex shunts blood away from the extremities and concentrates it around the brain and heart. Research published in the journal PLOS One in 2019 by Jeremy Goldbogen's team at Stanford University attached the first biologging tag directly recording heart rate from a free-swimming blue whale. What they found confirmed theoretical predictions, but still astonished the scientific community. The heart rate range in a diving feeding blue whale spans from 2 beats per minute at depth to as high as 37 beats per minute at the surface immediately following a deep dive. This is the largest heart rate range ever recorded in any animal, and it operates at the absolute limits of cardiac physiology. Now scale the animal up, double the mass. The heart must now pump blood through a body 8 times the volume with blood vessels whose cross-sectional area has only quadrupled. The pressure required increases dramatically. The wall thickness of the heart must increase, but cardiac muscle, like all muscle, has a maximum force output per unit of cross-sectional area, approximately 30 newtons per square centimeter, a value that is essentially constant across all vertebrate species. There is no evolutionary trick that changes this number. It is a property of the protein filaments, actin and myosin, that make muscle work. A whale significantly larger than the blue whale would require a heart that exceeds the force-generating capacity of cardiac muscle tissue. Full stop. No amount of natural selection can redesign the contractile proteins of muscle cells. The wall is not ecological. It is molecular. The second wall is respiratory, and it is equally unforgiving. A blue whale's lungs hold approximately 2,500 liters of air. The oxygen in that air must diffuse across the alveolar membranes into the bloodstream fast enough to support an animal that, during active feeding, is consuming energy at an extraordinary rate. The surface area available for gas exchange in the lungs scales with body size, but again, not fast enough. As body mass increases, the oxygen demand of the tissues grows faster than the lung surface area can grow. Marine mammals have evolved several adaptations that push the limits of oxygen management. Their blood contains exceptionally high concentrations of hemoglobin, the oxygen-carrying protein. Their muscles contain extraordinarily high concentrations of myoglobin, a related protein that stores oxygen directly in muscle tissue, which is why whale muscle is almost black in color. Research by Paul Ponganis at the Scripps Institution of Oceanography has documented oxygen store management in diving mammals in extraordinary detail, showing that cetaceans operate their oxygen stores with a precision that borders on the miraculous. But there is a hard limit to hemoglobin concentration in blood. Above a certain level, blood becomes too viscous to flow efficiently. The cardiovascular system would have to work harder to push it through the vessels, consuming the very oxygen it is trying to deliver. This is another molecular ceiling, not an engineering problem to be solved by evolution over time, a chemical and physical constraint built into the nature of biological fluids. The third wall is thermic, and this one is perhaps the least discussed but the most subtle. Water conducts heat approximately 25 times more efficiently than air. A warm-blooded animal in cold water is constantly losing heat to its environment. The blue whale's blubber layer, up to 50 centimeters thick in well-nourished individuals, is the primary defense against this loss. But blubber is also an insulator that traps heat during exercise. During intense lunge feeding, the whale generates enormous amounts of metabolic heat that must be dissipated or the animal will overheat and die. The countercurrent heat exchange systems in the fins and flukes, which we mentioned in the previous chapter, are the solution. But they have finite capacity. A larger animal generates more heat proportionally than a smaller one because metabolic heat production scales with volume while heat dissipation scales with surface area. The square-cube law again, arriving from a different direction. Make the whale significantly larger, and the heat exchange systems cannot keep pace with metabolic heat production during peak activity. The animal overheats during feeding, and an animal that overheats during feeding either stops feeding and starves, or continues feeding and dies of hyperthermia. These three walls, cardiovascular, respiratory, and thermic, converge at approximately the size of the blue whale. Not precisely at that size. The blue whale has not crashed into any of these walls. It is operating near all of them simultaneously, with margins that are small but real. It is, as one researcher memorably described it in a 2018 review paper in the journal Trends in Ecology and Evolution, a biological system at maximum sustainable complexity. But here is what makes this genuinely extraordinary. These physical and physiological walls would place the ceiling at roughly the current size of the blue whale regardless of ecological conditions. The ocean could be twice as productive as it is. The krill could be 10 times as and the blue whale still could not evolve to be significantly larger because the cardiac muscle, the hemoglobin concentration limits, and the heat exchange capacity would still impose the same constraints. The physics does not care about the food supply. And yet, and this is the twist that the latest research has made undeniable, ecology does impose its own ceiling. Separately, independently, and in some ways, the ecological ceiling is the more immediately dangerous one, because the physical ceiling is stable. It has been where it is for millions of years and will remain there regardless of what happens to the oceans. But the ecological ceiling, the ceiling imposed by the availability of dense, predictable krill patches in cold, productive water, is not stable at all. It is moving. Research published in the journal Nature Climate Change in 2022 by a team led by Evgeny Pakhomov at the University of British Columbia documented significant shifts in krill distribution and abundance in the Southern Ocean over the previous 4 decades. Krill populations in the southwest Atlantic sector of the Southern Ocean, historically the most productive blue whale feeding habitat on Earth, showed significant declines in mean density correlating with warming sea surface temperatures and changes in sea ice extent. The krill are not disappearing, but they are becoming less predictably dense, less concentrated, more variable in their distribution. And remember what we established in Chapter 2. The blue whale's lunge feeding strategy is only energetically profitable above a certain threshold of krill density. Below that threshold, lunging costs more energy than it returns. The animal starves in the middle of a sea full of food because the food is too sparse to harvest efficiently. This is not a theoretical projection. There is evidence that it is already happening. Body condition data from blue whales in the Southern Ocean, compiled from photographic and acoustic studies by researchers including Susanna Calderon at the Scottish Association for Marine Science, suggests that some populations of blue whales are showing reduced blubber thickness compared to historical estimates derived from whaling records. The animals are leaner. They are working harder for fewer calories. The margin between survival and starvation, already thin, is thinning further. Our whale, feeding in the Southern Ocean on this particular morning, is fortunate. She has found a good patch, a dense patch, the kind of patch that still exists in the Southern Ocean, that still makes the blue whale's extraordinary feeding strategy work the way evolution designed it to work. But she has approximately 3 hours left, and in those 3 hours, something is going to happen that will illustrate with brutal clarity exactly how thin the margin between the largest animal that ever lived and catastrophic failure actually is. Before we get there, we need to spend a moment with the question that lurks behind everything we have discussed so far. The question that, once you have understood the walls, the cardiac wall, the respiratory wall, the thermic wall, the ecological wall, becomes almost impossible to dismiss. The blue whale is at the ceiling. It has been at the ceiling for roughly 3 million years. In that time, it has survived ice ages, changes in ocean circulation, the evolution and extinction of countless competing species, and, in the last century, the most devastating direct assault by a single predator that any large vertebrate has experienced in the history of life on Earth. It survived all of that, and it is still here, still feeding, still calling, still breathing that towering column of mist into the cold morning air of the Southern Ocean. So the question is not really whether the blue whale can exist. We know it can. It is right there. The question is whether it can continue to exist in a world that is, right now, actively dismantling the oceanographic conditions that made it possible. And to answer that question fully, we need to understand what happened in the last 6 hours of one particular blue whale's life. Not as a tragedy, not as a cautionary tale, but as a data point, a moment of clarity, a window into the machinery of survival operating at the absolute extreme of biological possibility. The morning feeding is ending. Our whale surfaces for a long series of breaths, 4, 5, 6 slow exhalations, each one sending that misty column 9 meters into the air. Her metabolic rate is elevated. Her heart is beating at roughly 30 beats per minute, elevated from resting but well within normal post-feeding range. She is about to do something that will take her and us deeper into the nature of gigantism than anything we have discussed so far. She is about to dive into the deep, the physics of a living submarine. She tips forward. It is a movement of extraordinary grace for an animal of this size. The massive flukes rise clear of the water, gray-blue, mottled, as individually distinctive as a human fingerprint, cataloged in the blue whale photo identification database maintained by the International Whaling Commission and research institutions including the Cascadia Research Collective and the Argentine Instituto de Conservación de Ballenas. Then the flukes slip beneath the surface without a splash, without drama, and she is gone. The ocean closes over her as if she was never there. But what happens next, in the dark water beneath that calm surface, is one of the most physically demanding things any animal on Earth routinely does. And understanding it requires us to think carefully about what depth actually means for a body of this size. Pressure increases by approximately 1 atmosphere for every 10 meters of depth. At 100 meters, a shallow dive for a blue whale, the pressure on the outside of the animal's body is 11 times the atmospheric pressure at the surface. At 300 meters, well within the documented dive range of blue whales based on biologging data compiled by Bruce Mate at Oregon State University's Marine Mammal Institute across studies published through the 2000s, the external pressure is 31 atmospheres. 31 times the pressure at the surface. Now think about what that means for a body containing air spaces, the lungs, the sinuses, any gas-filled cavity in the body. At 31 atmospheres, the gas in those spaces is compressed to approximately 1/31st of its surface volume. The lungs of a blue whale at 300 meters depth contain air compressed into a space roughly the size of a large suitcase, compared to the room-sized volume they occupy at the surface. This compression is not incidental. It is not a problem to be solved. It is, in fact, part of the solution. As a blue whale descends, its lungs compress. This reduces the animal's buoyancy. The upward force of the water supporting the animal decreases as the air spaces shrink. At a certain depth, the whale becomes neutrally buoyant, neither sinking nor floating, suspended in the water column with no muscular effort required to maintain depth. Below that depth, it becomes negatively buoyant and sinks passively,
conserving the muscular energy that would otherwise be needed for active swimming downward. Research by Birgitta MacDonald and colleagues published in the Journal of Experimental Biology demonstrated that blue whales exploit this passive sinking during the descent phase of deep dives, gliding downward with minimal muscular activity once they pass the neutral buoyancy depth. The energetic saving is significant.
Over thousands of dives in a feeding season, this passive descent strategy likely saves enough energy to make the difference between a successful migration and a catastrophic caloric deficit. But the compressed lungs create a problem that took marine biologists decades to fully understand. At depth, as the gas in the lungs is compressed to high pressure, nitrogen from that gas begins to dissolve into the blood and tissues. The same phenomenon that causes decompression sickness, known colloquially as the bends, in human divers who ascend too quickly. As pressure drops during ascent, the dissolved nitrogen comes out of solution and forms bubbles in the blood and tissues. Those bubbles can block blood vessels, damage joints, and kill. Whales dive to extreme depths and ascend relatively quickly. They should, by all rights, suffer chronic decompression sickness. For years, scientists assumed they simply did not, that their physiology had somehow solved this problem completely. Then, in 2011, a paper published in the Proceedings of the Royal Society B by Michael Moore at the Woods Hole Oceanographic Institution and a team of colleagues reported evidence of decompression-related bone damage in the skeletons of stranded whales. Not catastrophic damage, not fatal damage, but real, measurable evidence of nitrogen bubble formation in bone tissue. The blue whale does not have a perfect solution to the nitrogen problem. It has a management strategy, a set of adaptations that reduce the risk to acceptable levels without eliminating it entirely. The collapsible rib cage, ribs connected to the sternum by flexible cartilage rather than rigid bone, allows the lungs to compress more completely at depth, reducing the volume of gas available for nitrogen dissolution. The selective circulation of blood away from peripheral tissues during dives reduces the surface area over which nitrogen can dissolve. The extraordinarily high myoglobin content of the muscles allows the whale to carry enough oxygen in the muscle tissue itself that it can shut down gas exchange in the lungs during a dive almost entirely. Together, these adaptations reduce nitrogen absorption dramatically, but they do not eliminate it. The blue whale lives with a low chronic level of decompression risk on every dive it makes. Another margin, another thin line between function and catastrophe. Our whale descends through 100 meters, 200. She is heading for the deep scattering layer, the diffuse band of organisms including krill, small fish, and other zooplankton that migrates vertically through the water column, rising toward the surface at night and sinking to depth during the day to avoid visual predators. In the Southern Ocean, this layer typically sits between 200 and 500 meters depth during daylight hours. At roughly 240 meters, she begins to level off. The biologging data from similar dives, published by Goldbogen and colleagues across multiple studies in the Journal of Experimental Biology and Marine Mammal Science, shows a characteristic pattern at this point. The whale is scanning, moving horizontally through the water column, using its sensory systems to locate the densest concentrations of prey. And here we encounter one of the most intriguing and least understood aspects of blue whale biology. How does a blue whale find krill at depth in the dark? The Southern Ocean at 240 meters depth receives essentially no sunlight. The krill aggregations down here are invisible in any optical sense, yet blue whales locate them with remarkable precision. They do not simply swim randomly through the deep scattering layer and hope to encounter a dense patch by chance. The biologging data shows purposeful navigation, animals moving in ways that suggest they know where the food is before they reach it. Several mechanisms have been proposed. Bioluminescence is one possibility. Krill and many other deep-sea organisms produce light, and a large aggregation of bioluminescent krill might produce a detectable glow even at these depths. Research by Edith Witter at the Ocean Research and Conservation Association has documented extensive bioluminescence in the deep scattering layer of various ocean regions, though direct evidence linking blue whale navigation to bioluminescent cues remains limited. Acoustic detection is another candidate. Krill swarms produce faint sounds, the clicks and snapping of thousands of small bodies moving through water. Some researchers have proposed that the blue whale's extraordinarily sensitive low-frequency hearing might detect these sounds at distance, providing acoustic imaging of prey distribution. A study published in 2012 in PLOS One by Marty Savalainen and colleagues explored this possibility, though the hypothesis remains unconfirmed. A third possibility, and perhaps the most intriguing, involves the whale's lateral line system, pressure-sensitive receptors distributed along the body that detect water movement. Dense krill swarms disturb the surrounding water in characteristic ways, and it is conceivable that a sufficiently sensitive pressure detection system could map these disturbances at distance. Research on this mechanism in large whales is still in its early stages. What is clear from the behavioral data is that blue whales are not random foragers. They make decisions. They navigate towards specific targets. They exhibit what the researchers at Stanford's Hopkins Marine Station in a 2019 paper in Science Advances described as prey field assessment behavior, periods of exploratory swimming at depth that appear to precede targeted lunge feeding events, as if the animal is mapping the prey field before committing to the energetically expensive business of lunging. Think about what that implies for a moment. An animal with a brain weighing approximately 6 to 7 kilograms, large by absolute measure, though small relative to its body size, is performing sophisticated spatial reasoning about a three-dimensional prey field in complete darkness at depth. It is weighing energy costs against potential returns. It is making decisions that, if wrong, could cost it the caloric equivalent of several hours of feeding effort. Is this intelligence? Is this consciousness? These are questions that science approaches with extreme caution, and rightly so. We cannot know what it is like to be a blue whale in the way that we can never fully know what it is like to be any other creature. But the behavioral sophistication documented in these animals by decades of careful field research is real and measurable. The decisions they make are not random. They are not simple reflexes. They are, at minimum, the product of a highly developed nervous system processing complex environmental information and generating adaptive responses. Our whale finds what she is looking for at 260 meters depth. The krill patch is not as dense as the surface aggregation she exploited this morning. Midday krill at depth tends to be more dispersed than the surface concentrations that form at dawn and dusk, but it is dense enough. Her sensory assessment, whatever form it takes, has determined that the energetic return will justify the cost of lunging at this depth, in this pressure, with the additional physiological demands imposed by depth. She accelerates. At 260 meters depth, a blue whale lunge feeding event is a phenomenon of almost incomprehensible scale. The pressure at this depth is 27 atmospheres. The water resistance against a body moving at feeding speed is enormous. The energy expenditure of a single lunge at depth is substantially higher than a surface lunge because the animal must work against both water resistance and the increased density of cold, deep water. And yet the return can be worth it if the patch is right. Research published by Goldbogen's group in the Journal of Experimental Biology in 2011 calculated the energetic return on investment for deep lunge feeding events and found that, in sufficiently dense prey patches, deep feeding could be as profitable as shallow feeding, despite the higher energy cost, because prey density at depth is sometimes higher than at the surface due to the vertical compression of the scattering layer during daylight. She lunges. Once. Twice. The water around her is a universe of compressed cold and darkness, and the chemical signatures of the krill she is harvesting. Her baleen filters. Her tongue pushes. Her massive body decelerates from feeding velocity to near stillness, and then begins to accelerate again for the next strike. 3 lunges at depth. 4. Then something changes. The krill patch thins, not gradually, abruptly. This is characteristic of deep scattering layer dynamics. The patches are not uniform clouds. They are discrete aggregations with edges, and when a large predator passes through them, the edges are reached quickly. Our whale has exhausted this particular concentration. The calculation shifts. Continuing to hunt at this depth, in this now sparse water, will cost more than it returns. She stops. She pivots with a movement that seems impossible for a body of this size, a slow sculling turn that repositions her heading toward the surface, and she begins to ascend. The ascent is where the nitrogen problem becomes most acute. The dissolved nitrogen in her blood and tissues, absorbed during the descent and the feeding period at depth, must be managed carefully as the pressure drops. Her circulation adjusts. The blood flow patterns that restricted nitrogen absorption during the dive now facilitate its careful, gradual release through the lungs as she rises. She does not ascend straight to the surface. The biologging data from multiple studies documents a characteristic blue whale behavior during ascent, a pause at intermediate depth, sometimes described as a drift phase, where the animal moves slowly and horizontally for several minutes before completing the ascent. The function of this behavior is not definitively established, but the leading hypothesis is that it represents a decompression management strategy. A built-in safety stop, evolved over millions of years, that reduces the rate of nitrogen bubble formation during ascent. The blue whale has its own decompression tables, written not in dive manuals, but in its DNA. She rises through 150 meters. 150. And then she is at the surface again, and the Southern Ocean opens around her, gray and vast and cold, and she blows. 1, 2, 3 long, slow exhalations, each one a column of warm vapor rising 9 meters into the air. The vapor is not just water. It contains mucus, cellular debris, bacteria, and traces of hormones and stress markers that researchers have recently learned to analyze for health information. A 2017 paper published in Scientific Reports by Karina Acevedo Whitehouse at the Universidad Autónoma de Querétaro and colleagues described the use of aerial drones to collect blow samples from free-swimming blue whales, a non-invasive method of health monitoring that has opened entirely new windows into the physiology of living animals. The blow tells us things, not everything, but and what those things reveal, when we look at the full picture of what we know about the blue whale's physiology, ecology, and evolutionary history, is a portrait of an animal that is simultaneously one of the most successful and most precarious large vertebrates on Earth. She has been at the surface for 4 minutes now. Her heart rate is elevated, but dropping. The nitrogen is clearing. The oxygen stores are rebuilding. She has approximately 2 hours left. And what is coming in those 2 hours is not another feeding dive. It is not another careful descent through the deep scattering layer. It is something that no amount of evolutionary refinement has fully prepared any blue whale to handle. It is us. The last 2 hours, when the world we built becomes a wall. She is at the surface, breathing, recovering, and somewhere approximately 40 kilometers to the northwest, a container ship is moving through the Southern Ocean at 22 knots. It is not hunting her. It is not aware of her. It is simply moving, as container ships do, along one of the great shipping lanes that cross the Southern Ocean between South America and Australia. It is carrying consumer goods, electronics perhaps, clothing, food, the entirely ordinary cargo of the global economy. Its crew of 23 people are going about their entirely ordinary routines. Nobody on that ship is thinking about blue whales. But the ship is producing something that travels much faster than its hull moves through the water. Sound. Low-frequency sound. The kind produced by large propellers turning at high speed, by the vibration of massive diesel engines, by the cavitation of water around the propeller blades. Sound that propagates through seawater with extraordinary efficiency. Sound that, in the frequency range of approximately 10 to 200 hertz, can travel hundreds of kilometers through the deep sound channel of the ocean with minimal attenuation. The same frequency range in which blue whales communicate. This is not a coincidence that anyone planned. It is a catastrophic overlap between the acoustic signature of industrial civilization and the communication bandwidth of the largest animal that ever lived. And it has been building, quietly and relentlessly, for over a century. Research published in the journal Science in 2009 by Mark MacDonald, John Hildebrand, and Sarah Wiggins at the Scripps Institution of Oceanography used long-term acoustic records from hydrophone arrays originally deployed by the United States Navy during the Cold War to track Soviet submarines. These arrays had been recording ocean sound continuously since the 1960s. When the researchers analyzed 50 years of acoustic data, what they found was deeply alarming. Low-frequency ocean noise in the North Pacific had increased by approximately 10 decibels between the 1960s and the 2000s. 10 decibels. In acoustic terms, that represents a 10-fold increase in sound intensity. The ocean, over the course of half a century, had become 10 times louder in exactly the frequency range that whales use to communicate, navigate, and find mates. The Southern Ocean, historically more remote from shipping lanes, has experienced smaller but still significant increases in ambient noise, and the trend continues upward as global shipping traffic increases year by year. The International Maritime Organization estimated in a 2020 report that global shipping traffic had increased by approximately 300% since 1990. 300% in 30 years. Our whale hears the container ship. We cannot know with certainty what she hears, whether it registers as a distinct object, a directional threat, a masking wall of noise that obscures the signals she is trying to detect. What we know from the research literature is that anthropogenic noise affects blue whale behavior in measurable ways. A study published in the journal Endangered Species Research in 2012 by Layla Hatch at the NOAA Stellwagen Bank National Marine Sanctuary and colleagues documented that shipping noise in the frequency range of blue whale calls reduced the effective communication range of those calls by as much as 63% in some ocean regions. The distance over which a blue whale call can be detected by another blue whale has been cut. in heavily trafficked ocean areas to roughly 1/3 of what it would be in a pre-industrial ocean. Think about what that means for an animal that navigates across thousands of kilometers of open ocean using sound, that finds mates using sound, that may use sound to coordinate the location of productive feeding grounds across entire ocean basins. The acoustic landscape of the blue whale's world has been compressed, fragmented, and partially destroyed within the span of a single human lifetime. She adjusts her calling behavior. This is documented. Research by Mariana Melcon and colleagues, published in PLOS One in 2012, demonstrated that blue whales in areas of high shipping noise increased the source level, the loudness, of their calls by up to 3 decibels in response to elevated ambient noise. They call louder to be heard. The way a person raises their voice in a noisy room. But calling louder costs energy. Energy that could go toward feeding. Energy that could go toward migration. Energy that is at the margins of survival that this animal operates within, not unlimited. The container ship passes. Its noise peak reaches our whale at approximately 1 hour and 40 minutes before the moment we are building. She has submerged again by this point, making another foraging dive, but shallower this time. The behavior that researchers describe as exploratory diving, prospecting for prey concentrations rather than committing to deep feeding dives. The noise does not stop her. It does not drive her away. But it changes her behavior in subtle ways that the biologging data captures with merciless precision. Her dive duration shortens slightly. Her swimming speed increases marginally. She surfaces more frequently, taking more breaths between dives than the pre-noise baseline. Small changes, each one individually trivial. Collectively, they represent an elevation in physiological stress that has measurable consequences for caloric balance. A 2019 study published in the Proceedings of the Royal Society B by Hannah Myers at the University of California, Santa Cruz and colleagues used a bioenergetic modeling approach to estimate the cumulative energetic cost of chronic noise exposure on blue whale feeding efficiency. Their model suggested that sustained noise exposure at levels typical of moderately trafficked ocean regions could reduce a blue whale's net energy acquisition during the feeding season by between 4 and 15%, depending on individual behavior and local conditions. 4 to 15%. In an animal already operating with thin margins, in an animal that needs to accumulate enough caloric reserves during a limited feeding season to fuel a migration of thousands of kilometers, to sustain itself through months of reduced feeding on the breeding grounds, and in the case of a pregnant female, to produce and nurse a calf that, at birth, already weighs approximately 2.5 tons. The margin does not accommodate a 4 to 15% reduction gracefully. But noise is not the only threat waiting in these last 2 hours. 45 minutes before the end, our whale is at the surface again, and she is in the path of something. Not the container ship, something smaller. A research vessel, as it happens, one of dozens that work the Southern Ocean each austral summer, collecting the oceanographic and biological data that forms the foundation of our understanding of this ecosystem. The irony is not lost on the scientists who study it. The very act of researching blue whales creates some of the same disturbances that threaten them. But research vessels are not the primary ship strike risk. The primary risk comes from large, fast vessels, container ships, bulk carriers, tankers, that move through blue whale habitat at speeds that make collision avoidance essentially impossible for both parties. A blue whale resting at or near the surface, recovering from a feeding dive, is acoustically invisible to a ship's sonar, which is designed for navigation not marine mammal detection. And a ship moving at 20 knots covers 100 meters in approximately 10 seconds. The whale, even if it detects the approaching vessel acoustically, has limited options for rapid evasion. Ship strikes are a documented and significant cause of blue whale mortality. Research published in 2019 in the journal Marine Pollution Bulletin by Sylvia Silber and colleagues at the National Marine Fisheries Service analyzed ship strike mortality data across multiple large whale species and found that blue whale populations on the United States West Coast, a population estimated at approximately 2,200 individuals, experienced ship strike mortality rates that could affect population recovery trajectories under some modeling scenarios. 2,200 individuals. The entire eastern North Pacific blue whale population, a number smaller than the audience at a medium-sized concert. And ship strikes are removing individuals from that population every year. The research vessel passes at 300 meters distance, close by open ocean standards. Our whale detects it and moves. Not in panic. Nothing in the behavioral data suggests the dramatic flight response that some cetaceans show in response to vessels. A gradual, measured course change. A deepening of the current shallow dive. An increase in horizontal displacement from the vessel's track. Energy spent on avoidance. Energy not spent on feeding. And now, in the final 30 minutes, we arrive at the deepest and most systemic threat. The one that does not announce itself with engine noise or a visible hull. The one that acts on the blue whale not in individual encounters, but across entire ocean basins, across entire seasons, across the fundamental ecological architecture that made the blue whale possible in the first place. The water is warming. Not dramatically, not in a way that our whale can detect directly, not in a way that feels like anything to an individual animal on an individual morning in the Southern Ocean. But the data is unambiguous, and the trend is consistent, and the consequences are becoming measurable in ways that matter enormously. The Southern Ocean has warmed by approximately 0.2 degrees Celsius in the upper 100 meters over the past 50 years, according to data compiled by the Intergovernmental Panel on Climate Change in its 2021 Sixth Assessment Report. 0.2 degrees sounds trivial. For a biological system calibrated to function within extremely narrow temperature windows, it is not trivial at all. And Arctic krill, Euphausia superba, are critically dependent on sea ice. Their larvae feed on the ice algae that grow on the underside of sea ice during winter. Without sufficient sea ice extent and duration, krill recruitment, the survival of juvenile krill into the adult population, falters. Research published in Nature in 2004 by Angus Atkinson at the British Antarctic Survey and colleagues, using data from net haul surveys spanning the previous 80 years, documented a significant decline in krill density in the southwest Atlantic sector of the Southern Ocean since the 1970s, correlating with declining sea ice extent. The Southwest Atlantic sector. The Bransfield Strait. The waters around South Georgia and the South Sandwich Islands. These are the most historically productive blue whale feeding grounds in the Southern Ocean, the places where the dense, reliable krill aggregations that make lunge feeding so profitable have historically been most abundant and most predictable. And they are changing. The krill are not gone. They are not even close to gone. The Southern Ocean still supports an estimated krill biomass of between 100 and 400 million tons, one of the largest concentrations of any single animal species on Earth. But the distribution is shifting. The density patterns are becoming less predictable. The window of peak productivity is changing in its timing relative to the blue whale's migration schedule, which is itself an evolved behavior calibrated over millions of years to the historical seasonal patterns of the Southern Ocean. A 2020 study published in Global Change Biology
by Emma Sporing and colleagues, modeled the consequences of projected ocean warming and sea ice loss on blue whale habitat suitability in the Southern Ocean through the end of the 21st century. Their projections suggested a significant southward shift in optimal blue whale feeding habitat, compressing it toward the Antarctic continent and reducing the total area of high-quality habitat by between 20 and 30% under moderate warming scenarios. 20 to 30% of the habitat that allowed this animal to evolve to its current size. Gone.
Within the lifetime of blue whales alive today, our whale feeds. She has made 2 more shallow feeding dives in the last 30 minutes, finding modest prey concentrations that return a positive energetic yield, but nothing like the exceptional patch she found at dawn. Her daily caloric intake, when the biologging data from this kind of day is modeled bioenergetically, is probably running at roughly 60 to 70% of the maximum she would achieve on an exceptional feeding day. Sufficient. Probably sufficient. On this day, in these conditions, for this individual who is in good body condition and whose blubber reserves are building from their post-migration low. But sufficient is a word that contains multitudes when you are talking about an animal operating at the absolute limits of biological possibility in an ocean that is changing faster than evolution can respond. She surfaces for the last time in our 6-hour window. The sun has moved significantly across the sky. The Southern Ocean around her is the same, gray, cold, immense, indifferent. The container ship is long gone, its noise fading into the general ambient roar that now underlies all ocean sound everywhere on Earth. The research vessel has moved on. She blows. That column of mist rises into the cold air. And in this moment, this specific, ordinary, extraordinary moment, she is the largest animal that has ever lived on this planet. Not a fossil, not a reconstruction, not a statistical abstraction. A living system of 190 tons, breathing, processing, deciding, surviving. For now. The question that has been building through everything we have discussed, through the square-cube law and the cardiac limits and the krill ecology and the acoustic masking and the warming ocean, that question now demands its answer. Why will nothing ever be this big again? That is where we are going, to the final chapter, to the synthesis of everything we have learned, to the evidence that the blue whale is not just the largest animal that has ever lived, but almost certainly the largest animal that ever will live, for reasons that are written in physics and ecology and the irreversible trajectory of a planet that has, in the space of 2 centuries, fundamentally altered the conditions under which biological gigantism is possible. The flukes rise. The ocean closes. She is gone. Why nothing will ever be this big again. Let us take stock of what we know. We know that the blue whale reached its current size through a specific, unrepeatable convergence of circumstances, a continent drifting into polar position, an ocean current establishing itself around that continent, a productivity regime emerging from that current that concentrated food in the precise way that made extreme gigantism energetically profitable. A lineage of mammals already committed to the ocean, already filter feeding, already large, that found itself in the right place at the right time with the right tools to exploit an ecological opportunity that had never existed before in the history of life on Earth. We know that this convergence took roughly 53 million years to produce, and that the final, most extreme phase of gigantism, the phase that produced the blue whale as we know it, took only 3 million years. A geological sprint, a rapid evolutionary response to a specific, narrow ecological window. We know that the animal that emerged from this process is operating simultaneously at the limits of cardiac physiology, respiratory capacity, thermal management, and ecological dependence on prey density, that it has essentially no margin for error in any of these systems, that it exists right now in a state that one researcher called maximum sustainable complexity, a phrase that contains within it both admiration and warning. And we know that the conditions which created this animal are changing, faster than evolution can respond, in directions that systematically degrade the ecological foundations of the blue whale's existence. So the question is not mysterious. The answer, when you lay out all the evidence, is not ambiguous. Nothing will ever be this big again. But let us be precise about why. Because there are multiple reasons, and they operate on different timescales, and understanding each one separately makes the conclusion not just more convincing, but more profound. The first reason is physical, and it is permanent. The square-cube law does not change. The maximum force output of cardiac muscle does not change. The maximum oxygen carrying capacity of hemoglobin in biological fluids does not change. The heat exchange capacity of biological tissues does not change. These are not contingent facts about the current state of the world. They are properties of matter and energy and the chemistry of life that will remain constant for as long as life as we know it exists on this planet. The blue whale has reached the size at which these physical constraints converge. Any animal significantly larger would face cardiovascular failure, respiratory insufficiency, or thermal collapse during peak activity. This ceiling has existed since the blue whale reached its current size 3 million years ago. It will exist 3 million years from now. It is not a wall that a future evolutionary lineage could find a way around, because it is not a wall built of contingent ecological circumstances. It is built of physics. Could a hypothetical marine animal evolve a fundamentally different body plan that circumvents these limits? Could some future lineage develop a circulatory chemistry that carries more oxygen than hemoglobin? Could evolution produce a cardiac muscle with higher force output per unit area? These are questions that theoretical biologists take seriously, and the honest answer is probably not, within the constraints of carbon-based biochemistry as we understand. The proteins that carry oxygen in blood have been subject to billions of years of evolutionary optimization across countless lineages. The contractile proteins of muscle have been similarly refined across the entire history of animal life. If there were a significantly better solution within the chemical space available to biological systems, evolution would very likely have found it already. The fact that all vertebrate lineages across 500 million years of independent evolution converge on essentially the same molecular solutions for these problems is strong evidence that those solutions are near optimal within the available chemical space. The physical ceiling is not just a ceiling for the blue whale. It is a ceiling for life on Earth. The second reason is ecological, and it operates on a timescale of centuries to millennia. The oceanographic conditions that made blue whale gigantism possible were the product of a specific planetary configuration: Antarctica in polar position, the Drake Passage open, the Antarctic circumpolar current established, glacial interglacial cycles producing seasonal productivity patterns of extraordinary intensity. These conditions have existed, in their current form, for roughly 3 million years. They will not exist in their current form indefinitely. We are already in the early stages of their disruption. The evidence is in the sea ice data, in the krill recruitment data, in the ocean temperature records,
in the distribution shifts documented by Atkinson and colleagues, by Pakomov and colleagues, by the long-term monitoring programs of the British Antarctic Survey and the Australian Antarctic Division. The Southern Ocean is changing. The productivity patterns that make lunge feeding profitable at blue whale scale are becoming less reliable, less intense, less geographically predictable. This does not mean the Southern Ocean will stop being productive.
It will remain one of the most biologically rich ocean regions on Earth for the foreseeable future. But the specific character of that productivity, the dense, predictable, seasonally concentrated krill patches that make it possible to harvest 90 cubic meters of water and extract a profitable meal from it in less than 10 seconds, that specific character is being degraded by warming temperatures, declining sea ice, and the cascading ecological consequences of both. An ecological niche that is degraded does not necessarily disappear overnight. It shrinks. It becomes less reliable. The animal adapted to exploit it finds itself working harder for diminishing returns. Over generations, if the degradation is sustained, the population declines. The gene pool narrows. The evolutionary flexibility that might allow adaptation to new conditions is reduced. And eventually, the niche and the animal that filled it both contract toward a new, smaller equilibrium, or toward extinction. We are watching this process begin in real time with the blue whale. The global blue whale population, which has been recovering slowly and unevenly since the 1966 hunting ban, is currently estimated at between 10,000 and 25,000 individuals worldwide. The wide range of that estimate is itself significant. It reflects the genuine difficulty of counting animals that spend most of their lives underwater, spread across entire ocean basins, in a species whose low reproductive rate means that population surveys must be conducted over years to capture meaningful data. 10,000 to 25,000 individuals of an animal whose pre-whaling population was perhaps 250,000. Even at the high end of current estimates, the population stands at roughly 10% of its historical level, after nearly 60 years of protection. The recovery has been real, but agonizingly slow. Blue whales reach sexual maturity at approximately 5 to 15 years of age and produce a single calf every 2 to 3 years under good conditions. The maximum plausible rate of population increase, even in a fully protected population with optimal food availability, is estimated at approximately 4 to 7% per year. Research published in 2020 by Trevor Branch at the University of Washington, one of the leading experts on cetacean population dynamics, suggested that some populations, including the Chilean blue whale population, may be recovering at closer to the lower end of that range, implying full recovery timescales measured in decades to centuries, even under optimistic assumptions. Decades to centuries, during which the ocean is warming, during which the krill are shifting, during which the ship traffic is increasing, during which the acoustic environment continues to degrade. The third reason is evolutionary, and it is perhaps the most subtle of the three. Evolution requires time. It requires populations large enough to contain meaningful genetic variation. It requires stable selective pressures that act consistently across many generations. It requires, above all, the existence of the ecological niche toward which selection is pushing the organism. The blue whale took 3 million years to reach its current size from already large masticete ancestors. 3 million years of consistent selective pressure toward larger size, driven by the consistent profitability of larger body size for lunge feeding in a stable, productive Southern Ocean. The genetic and developmental machinery that produces a blue whale,
the regulatory genes that control growth, the hormonal systems that coordinate development, the ecological behaviors that are partly learned and partly innate, all of this complexity accumulated over millions of generations. If the blue whale were to go extinct tomorrow, what would replace it? Nothing. Not on any timescale relevant to human civilization. Not on any timescale relevant to the current phase of Earth's ecological crisis. The evolutionary pathway that produced the blue whale required a specific starting point, a lineage of large baleen whales already committed to filter feeding, already large, already in the Southern Ocean. It required a specific ecological context, the Southern Ocean at peak Pleistocene productivity. And it required millions of years. None of those conditions can be recreated. The lineage of large baleen whales still exists, but it has been devastated by whaling. The Southern Ocean is changing in ways that reduce rather than increase the selective pressure toward gigantism. And the millions of years of evolutionary refinement, cannot be compressed or recreated. This is the third wall, not physics, not ecology, time itself. And so we arrive at the conclusion that the evidence demands. The blue whale is not just the current record holder for largest animal. It is almost certainly the permanent record holder. Not because life has reached some absolute limit of imagination or possibility, but because the specific, contingent, irrepeatable combination of circumstances that produced this animal will not occur again on this planet. The Antarctic circumpolar current will not establish itself again. It is already established and will persist until continental drift changes the geometry of the Southern Ocean, on timescales of tens of millions of years, by which point the conditions will be entirely different. The Pleistocene glacial cycles that created the intense seasonal productivity patterns of the last 3 million years are being disrupted by human activity faster than biological systems can. And the lineage of large baleen whales, shaped by 53 million years of ocean life, into the only group of animals that ever found a way to push against all the physical and ecological walls simultaneously and survive. That lineage is still here, still breathing, still feeding, but diminished. Diminished to a degree that the fossil record will record as one of the most dramatic population collapses of a megafauna species in the entire Cenozoic era. Not caused by an asteroid, not caused by volcanic winter, not caused by the slow grinding of geological change, caused by us. By exploding harpoons and factory ships, and a few decades of industrial efficiency applied to the problem of killing the largest animals on Earth. We did not know when the whaling industry reached its 20th century peak that we were hunting the largest animals that had ever existed or ever would exist. We did not appreciate that what we were rendering into oil and fertilizer was not just a resource, but a biological miracle 3 million years in the making. The men on those factory ships in the Southern Ocean in the 1950s and 60s were not monsters. They were doing what industrial economies do. They were harvesting a resource efficiently until a resource was gone. But the resource was not replaceable. It was not renewable on any timescale that matters to us. It was, in a sense that we are only now fully beginning to understand, unique in the history of life on Earth. And here is where the story refuses to end in pure tragedy, because the blue whale is still here. 10,000 to 25,000 individuals scattered across all the world's oceans, still feeding, still calling, still making those extraordinary dives into the deep scattering layer, still producing those towering columns of mist in the cold air of the Southern Ocean,
still performing the most energetically profitable feeding behavior ever documented in a vertebrate. Our whale, the Category A female whose 6 hours we have followed today, is real. Not an individual we can name. The Southern Ocean population is too large and too dispersed for that kind of individual tracking in this narrative. But she is representative of something real, of thousands of animals still doing what the blue whale has been doing for 3 million years, still pushing against the walls, still surviving with thin margins in a world that has become, in the last 2 centuries, significantly harder to survive in. The recovery of the blue whale population, slow and uncertain as it is, represents one of the few genuine conservation successes in the history of large vertebrate protection. The international ban on commercial blue whale hunting, in place since 1966, prevented the extinction of the species. That is not a small thing. That is, in fact, an extraordinary thing. We came extraordinarily close to eliminating the largest animal in the history of life on Earth. And we stopped. Not in time to prevent catastrophic population collapse, but in time to prevent extinction. That distinction matters. Extinction is forever. Catastrophic population reduction is recoverable, given time and the right conditions. The blue whale genome is still in the world. The behaviors are still being learned and passed between generations. The evolutionary potential, though reduced, is not gone. What happens next depends on choices that are being made right now. Not choices about whaling. That battle, at least in its most acute form, has been won. The choices that matter now are about shipping lanes and noise reduction technology and greenhouse gas emissions and krill fishery management and the protection of critical feeding. Research published in 2021 in the journal Science by Matthew Lewis and colleagues proposed specific, actionable measures for reducing ship strike mortality in blue whales, including dynamic speed restrictions in known feeding areas during peak occupancy periods. Several shipping companies and port authorities have already voluntarily implemented speed reductions in blue whale habitat. The Port of Los Angeles and the Port of Long Beach launched a voluntary speed reduction program in 2014 that, by 2019, had been adopted by the majority of container shipping companies using those ports. It works. Ship strike mortality in participating vessels dropped significantly. The technology for quieter propellers exists and is being implemented in new vessel designs. The knowledge of where blue whales are and when, built up by decades of tagging and acoustic monitoring research, is being integrated into ship routing systems in real time. These are not solutions. They are mitigations. The fundamental challenges, ocean warming, krill distribution shifts, the slow pace of population recovery against a backdrop of accelerating environmental change, remain. But they demonstrate something important, that the trajectory is not fixed, that the choices we make in the next decades will determine whether the blue whale population recovers towards something approaching historical levels or whether it continues to exist as a ghost of its former ecological presence. Technically not extinct, but reduced to a remnant that can no longer perform its full ecological function. Because the blue whale is not just a record holder. It is an ecosystem engineer. Its feeding activity fertilizes the surface ocean. Whale feces are rich in iron and nitrogen, nutrients that stimulate phytoplankton growth, which in turn supports the krill that feed the whale. Research published in 2010 in PLOS One by Joe Roman at the University of Vermont and James McCarthy at Harvard University described this process, the whale pump, and estimated that the historical blue whale population may have significantly enhanced Southern Ocean productivity through nutrient cycling. The collapse of that population removed a major biological pump from the ocean's nutrient cycling system. The recovery of that population would restore it. The largest animal in the history of life on Earth is also, it turns out, a keystone of the ecosystem that created it. Remove it, and the ecosystem degrades. Restore it, and the ecosystem benefits. The blue whale is not just a passenger in the Southern Ocean. It is part of the machinery. So let us end where we began. On the surface of the Southern Ocean, with a single blue whale breathing. She has fed. She has dived. She has navigated. She has called into a noisier ocean than any blue whale has ever had to call into before. She has managed her oxygen, her nitrogen, her thermal balance, her cardiac output, her caloric budget, all simultaneously, all at the edge of what biological systems can sustain, all with the quiet, continuous precision of 3 million years of evolutionary refinement. She is the largest animal that has ever lived on this planet. She is, by the measure of body mass, the most extreme product of evolution that the biosphere has ever produced. She is the answer to the question of how big life can get, written in living tissue and warm blood, and the particular blue-gray color of deep water light falling through a massive body. And she is fragile. Not in the way that small things are fragile, not delicate or easily broken. Fragile in the way that extreme things are fragile. Fragile the way a system operating at maximum sustainable complexity is fragile. The way anything is fragile when it has no margin left. The flukes rise one more time. The ocean closes over them. She descends into the cold, dark, increasingly loud, increasingly warm Southern Ocean. And we are left on the surface, watching the ripples spread and fade, thinking about what it means to share a planet with something this extraordinary. What obligations that creates. What it would mean to lose it. What it would mean, what it still could mean, to save it. The largest animal that ever lived is not a fossil. Not yet. It is down there right now in the dark water, feeding and calling and surviving at the edge of the possible. The question is whether we will give it the ocean it needs to keep doing that. That question does not have a scientific answer. It has a human one. Leave your thoughts in the comments. What do you think the future holds for the blue whale? What should we be doing that we are not? And if this investigation changed how you think about the scale of life on this planet, about what evolution can produce and what we can destroy, and what we might still choose to protect, then share it. Because the story of the blue whale is not just natural history. It is a mirror. And what it shows us about ourselves is worth looking at carefully. Future holds for the blue whale. What should we be doing that we are not? And if this investigation changed how you think about the scale of life on this planet, about what evolution can produce and what we can destroy, and what we might still choose to protect, then share it. Because the story of the blue whale is not just natural history. It is a mirror. And what it shows us about ourselves is worth looking at carefully.